Hi friends, here in this video I'll be explaining the problem on velocity and acceleration in mechanisms. So let's get started. Now here is the question in front of us. It is given, figure shows the mechanism of a radial valve gear. The mechanism is given here. Crank OA rotates uniformly at 150 rpm. Here we can see there is crank OA rotating in an anti-clockwise direction with 150 rpm. Then dimensions of the various links are given here. OA link is of 150 mm. A to B distance, this link is 550 mm. Then A to C distance is 450 mm. And DC is 500 mm. And BE is 350 mm. Here we have to determine the velocity and acceleration of slider E. So in short we can say that when this crank OA would be rotating, that is the crank is the driving member, finally the motion would be transmitted to this slider, which is slider E, and it would be reciprocating. It would reciprocate along this line of stroke. So we have to find out how much is the velocity and acceleration of this slider. So that's the question. So the question is, we have to find the velocity and acceleration of slider E. Now when we are solving the problem related to velocity and acceleration in mechanisms, the first step is to draw the configuration diagram. That is, whatever the mechanism is given, that needs to be drawn again, and then we can go for the velocity and acceleration part. So here I'll draw the configuration diagram. So step number 1 is the configuration diagram, and when we look at the dimensions here, the dimensions are like it is 150 mm and then the major dimension is 550 mm. So it comes out to be 55 centimeter, and this is a very big value. So what I would be doing here is I would be drawing this diagram by taking a scale of 1:10. You can take the scale anything, like you can make it in quarter scale or half scale. Here I am taking the dimensions and the scale in the form of 1:10. So whatever the dimensions are there, they would be reduced by or divided by 10. So in the configuration diagram, the scale is 1:10. Then I'll be drawing this configuration. Now we can easily see that the distance between point O and the line of stroke of the slider is 550 mm. So on a scale of 1:10, this 550 mm would become 55 mm, that is by dividing by 10. So first I'll draw two horizontal lines. So this is 55 mm. Then the vertical distance between point O and point D is 200 mm. So that when I divide it by 10, it becomes 20 mm. So I would be drawing another line by taking a vertical distance of 20. Then I am selecting a point which will represent point O, and as we see, this crank OA is having an angle of 30 degree. So from point O, I'll take an angle of 30 degree. I'll draw a light line. Next, crank OA is given as 150 mm. So when I divide it by 10, it comes out to be 15 mm. So taking the radius as 15 mm in the compass, here I have taken 15 mm radius, keeping it on point O. Here I have drawn a light circle. The angle is 30 degree here, and this gives me crank OA. Now after drawing the crank, the next step would be I locate this point D, and from point O it is at 500 mm, that is when I divide it by 10 it comes out to be 50 mm. So from point O I am measuring 50 mm, and then I would be projecting it light upwards to get point D. After locating point D, here we can say AC is given as 450 mm, so that will be 45 mm for us on a scale of 1:10. Then DC is 500 mm, which will be 50 mm. So what I'll do here is measuring distance AC, that is 45 mm in the compass, keeping on point A and drawing a light arc. Then from point D I would be measuring CD as 50 mm because here it is 500. So measuring 50 mm. Now keeping it on point D, cutting this arc. So here I get point C at the intersection. Then on this same line that is on AC we have point B. AB distance is 550 mm, so A to B is 55 mm for us on a scale of 1:10. So AC already we have 45 mm. I would be extending this line again by 10 mm distance onto the same line. So AB distance is 55 mm. Then B to E distance, link BE is 350 mm. So that would be 35 mm for us, and cutting the line of stroke. Keeping on point B, I'll cut the line of stroke to get point E. Joining B and E. So here is this piston or slider E, which would be reciprocating in this horizontal plane along the line of stroke. So here I have given all the dimensions and drawn the configuration diagram for the given figure. In the figure they have given that this crank OA is rotating in an anti-clockwise manner, having a speed of 150 rpm. So that I'll write in the data, since speed of crank OA is 150 rpm, so therefore its angular velocity would be 2 pi n for link OA by 60, 2 pi n by 60, and therefore n is 150 divided by 60. So therefore the angular velocity OA comes out to be, it is 15.71, radian per second. Now after getting the angular velocity, I'll calculate the linear velocity for this link OA, because that would be required in the velocity diagram. So therefore the linear velocity is equal to angular velocity of the link multiplied by the link length. The length of OA is given as 150 mm. So therefore velocity of link OA comes out to be, it is 2356.5 mm per second. Now remember, when we have such big values, try to reduce the value by converting mm per second into meter per second, that is dividing by 1000. So therefore VOA would be 2.35, or we can say 2.36 meter per second. So this is the value which I would be using for the velocity diagram. Now after getting the linear velocity of link OA, the next step is, after configuration diagram, is the velocity diagram. Now for the velocity diagram, here we have the linear velocity as 2.36 and we are going to start with this velocity. So how to select the scale? First I am explaining that. This velocity is 2.36 meter per second. I'll try to fit this within, we can say 6 or 8 centimeters, anything, or even 5 centimeter would do. Now here I am taking the scale as I would be fitting 2.36 meter per second is equal to 8 centimeter. So therefore 2.36 divided by 8, that gives me the value as 0.295. So 1 centimeter is equal to 0.295 meter per second. This is the scale for the velocity diagram. I'll write it over here. And this scale should look proportionate, so I have taken it as 8 centimeter. Now how to draw the velocity diagram? For that, first I'll take the reference points, that is the fixed point O, and we can see D. These are the fixed points about which the crank OA is rotating. So fixed points O and D. And now when the crank is rotating in an anti-clockwise manner, as we see here, the linear velocity is always perpendicular to the link. So for that, on this link I'll take a perpendicular line that is measuring 90-degree angle with respect to point A. Now this vector VOA is representing the velocity of point A with respect to point O, or in short the velocity of link OA, and it is perpendicular to the link. Since it is rotating in an anti-clockwise sense, therefore the velocity vector is towards this side. If it would have been clockwise rotation, then the velocity vector would have been onto the opposite side. So here is the direction of the velocity vector, and at the same time we know this velocity is 2.36 meter per second, which I would be taking it as 8 centimeter. So drawing a line parallel to VOA, drawing a light line, then over this I would be measuring a distance of 8 centimeter, and here I am getting point A. This vector would be representing the velocity of point A with respect to O, that is VOA, which I have drawn here. Next, after getting VOA, since it is coming in this direction, and we can see here the crank and this connecting rod AB, They are connected at point A, and between them there is a turning pair. So when OA goes towards this side, AB would be shifted onto the other side. So it means its velocity vector would be perpendicular to the link. On the link, anywhere we can take a point. Like example, I am taking a point over here, measuring 90 degree. Now this would be the velocity vector of, we can say, link AB as well as link AC. The velocity vector is pointing towards this side. So for both of them, the velocity vector would be here. I'll say this is velocity vector V AB, or it can be even be VAC, perpendicular to the link. So when VOA goes onto the other side, VAB goes over this side, because they are forming a turning pair. Then just parallel to it, I'll draw a line through point A. A light line. Then after drawing this light line, over this line I am going to get points C and B, but here we don't know the values or the magnitude of the velocity VAB or VAC. We just know the direction, it is towards this side. So in order to get that, first what I would be doing here is, we have another link which is CD, and here there is D, which is called as the fixed point. So from D, if I can get a line which would be cutting this line which shows the velocity of AB or AC, so when through a line which is passing through point D, it would be cutting this line, I am going to get point C. In other words, the velocity vector for CD would be perpendicular to the link. I can take the point anywhere on this link. It has to be perpendicular. Then drawing a light line through it, light perpendicular line, which shows the velocity vector for link CD. Already point D is known to us. So now when I draw a line parallel to this velocity vector, now where it is cutting this line which is passing through A, at the intersection I would be getting point C, and this is the velocity vector for AC. Then here is the velocity vector for CD. Now once I have got point C, then B is on this same line which is passing through A and C. For that I would be using the concept of similarity. That is, I can say that since here AC distance is known to us, or I can say in other words, we require point B, so I can write it in this way, like capital AC upon capital AB is equal to small AC upon small AB, using the concept of similarity. From the configuration diagram, capital AC by capital AB, from the velocity diagram, small AC by small AB. So therefore capital AC is given as 450 mm, capital AB is 550, small AC I am going to measure it over here. It is 2.6 centimeters. So small AB would be calculated from here. Small AB would be 2.6 into 550 divided by 450. It comes out to be 3.18 centimeters. So from point A, I'll measure 3.18 centimeter, approximately 3.1 or 3.2 we can say approximately. So that gives me point B, which is here. Now after getting point B, the link which is left is link BE, and obviously the velocity vector would be upward, because when the velocity vector of BE would be upward, after that the slider is reciprocating with respect to the fixed guides, and fixed guides are denoted by O and D. These are the fixed points. So from O and D we are going to draw a light horizontal line, and the intersection would give us the velocity of this slider. So first of all I'll explain. On BE link I am taking any point perpendicular to that point on the link. This would represent the velocity of link BE. So here the velocity vector for link BE is perpendicular to the link, and here we have point B. So drawing a line which is parallel to this velocity vector, drawing a light line. Now from these fixed points O and D, a light line would be projected horizontally, because the velocity, linear velocity of the piston or the slider is along the line of stroke, that is horizontal. Drawing a horizontal line from points O and D, because they are the fixed points. This intersection gives me point E. Here we have point B, and this velocity vector is for link BE. And O to E distance represent the velocity of the slider or the velocity of the piston. So here the velocity diagram gets completed. Now the question is, we have to find the velocity of slider E. So for that I'll write down that from this velocity diagram, the first thing which I'll find is the velocity of slider E. It is distance OE into scale. O to E distance I'll measure here in terms of centimeter. It is approximately 2.9 centimeters. So 2.9 into the scale, which is 0.295. So therefore velocity of slider E will come out to be it is 0.855, which I'll write it as 0.86 meter per second. And that's the first answer. Now after getting the velocity of slider E, the next thing would be I would be calculating all the velocities here, because those would be required in the acceleration diagram. So it is better to calculate all the velocities. In this diagram I can say that velocity of OA is known to us, then velocity of slider E is known. Now I would be calculating the velocity of this connecting rod AB. So the next step would be velocity of link AB is equal to this small distance AB into the scale. Distance AB I'll measure in centimeters. It comes out to be 3.3 centimeter into the scale, which is 0.295. So therefore VAB comes out to be 0.97 meter per second. After getting velocity of AB, next I'll calculate velocity of link CD. Which is distance C to D into scale. Here we have distance CD. CD, I'll measure it in terms of centimeters. C to D distance. It is 6.4 centimeters into 0.295. So velocity of CD link comes out to be, it is 1.89 meter per second. Next, I'll be calculating the velocity of link BE, which is VBE, and I can write it over here. VBE would be equal to the small distance BE into scale, distance B to E is shown by this velocity vector. This also comes out to be 6.4 centimeter into scale 0.295. So therefore VBE, or velocity of link BE, is same as CD, which is 1.89 meter per second. Next, once I have found out all the velocities, I can say that the velocity diagram has been completed. And remember, whenever you are solving by using the graphical method, there are chances of getting the answers as approximate, because the answers won't match, because this is a graphical method. There may be some errors, so in such cases at least plus or minus 10% error is allowed, because of it being a graphical method. So you may not get the exact answers depending upon the way in which we are drawing it. So we have to remember that the answers won't be spot on for everyone. Next, after completing the velocity diagram, I would be going for the acceleration diagram, and for that all these velocities are required. Now into the acceleration diagram, I'll explain. First we need to draw a table, which I'll draw here. Now in these, writing the various columns, the first column is for the link, next is link length in terms of meter, then is the velocity of the link in terms of meter per second. After that, centripetal acceleration, which is A suffix C, given by formula velocity square upon the link length. I'll say link length is denoted by capital L. Unit would be in terms of meter per second square. After centripetal acceleration will be tangential acceleration, which is alpha, that is angular acceleration into the link length denoted by capital L, and the unit would be meter per second square. So these are the columns which are required for drawing the acceleration diagram, and I'll just explain how to fill this table. Now starting with the first column, that is link, in that we have to write down the link number 1, or here we can say the crank, because the crank is being the driving member. So link OA would be written first. Its length in terms of meter, OA is 150 mm, in meter it comes out to be 0.15. Then its velocity we have calculated, it was 2.36 meter per second. Then its centripetal acceleration, which is velocity square divided by the link length, so 2.36 square divided by 0.15. It is 37.13 meter per second square. Then for tangential acceleration we require angular acceleration, and since in this problem the angular acceleration of crank OA is not given, so we can take it as 0. It means the centripetal acceleration is the main acceleration for link OA and tangential acceleration is 0 because angular acceleration alpha is not given. Then after link OA is connected to link AB. Now its length was given as 550 mm in the data. This AB is 550 mm, so it comes out to be, it would be 0.55 meter. Then velocity of link AB, and that is why we have found the velocity, because it would be used in the acceleration diagram. So VAB is 0.97 meter per second. Centripetal acceleration, velocity square divided by link length again. It is 1.71 meter per second square. Now for link AB, here also we don't have the angular acceleration given, but it will be there, it will be present. So right now we don't know the magnitude or the value of tangential acceleration for AB. So I am writing a question mark here because this value we don't have right now. Then I would be going further. After AB, we have link CD and BE which are left. CD and BE. So link CD, its length is given. CD was 500 mm, so that comes out to be 0.5 meters. Its velocity of CD is 1.89 meter per second. Then its centripetal acceleration, velocity square divided by link length, 7.14 meter per second square. And similarly here also we don't have the value of angular acceleration, so tangential acceleration magnitude is not known right now, but we can find it out. Then we are left with link BE. Now the length of BE was given, it was 350 mm, so that comes out to be 0.35 meter. The velocity of link BE, it is 1.89 meter per second. Next, similarly centripetal acceleration 1.89 square divided by 0.35. It is 10.21 meter per second square. And again the tangential acceleration magnitude is not known, but we can find it out. At last the slider E is left, and for the slider, since it is sliding or reciprocating in a horizontal plane, then its acceleration would also be along this horizontal line. And for slider we don't have the length of the slider and all, so that won't be there into the table. So with the data available, now we can easily start the acceleration diagram. I'll first explain how to get the scale for the acceleration diagram. See, remember, whenever we are drawing acceleration diagram, check for the major dimension or the maximum value. Here I am getting 37.13 as the maximum value, so this would be the reference for me, and this value I am going to fit it in 8 centimeters. You can even fit into 6, 5 or 4 centimeter, but the diagram should look proportionate. So here I'll say that the scale is scale for the acceleration diagram. 37.13 meter per second square would be fit into 8 centimeters. So therefore 37.13 divided by 8, this value comes out to be 4.64. So it means the scale is 1 centimeter is equal to 4.64 meter per second square. Now this scale would be used for the acceleration diagram. And just when we are drawing the acceleration diagram in a similar manner like we have drawn the velocity diagram, taking O and D, that is the fixed points first. So I am taking points O and D which are fixed, and starting with the centripetal acceleration for link OA. Centripetal acceleration is 37.13, and centripetal means it would be acting towards the center. So the centripetal acceleration for OA would be passing to its center, that is A towards O. It would be like this centripetal acceleration of link OA, which is A towards O because it is pointing towards the center. So now we know the direction of the centripetal acceleration. So drawing a line parallel to OA from the fixed points, which is O and D, drawing with the help of light line. Drawing a light line. Now we know the value of centripetal acceleration of OA, and we have taken it as the reference for the scale. So 37.13 would be fit into 8 centimeter. So from point O, I am going to measure 8 centimeter distance. This will give me point A. And here is the centripetal acceleration for link OA. At the same time, we can say link OA is not having the tangential acceleration because angular acceleration is not given, so it is 0. In other words, this line OA would be representing the actual acceleration or the main acceleration for the link OA. Then after getting point A, the next thing would be looking at link AB. And again for AB also, its centripetal acceleration would be acting towards the center. Since AB and OA are connected, they are common center. Here I can say O is the center, which is the center of rotation for the crank. So the centripetal acceleration of AB will be along this connecting rod, and it would point towards point O. So this is the direction for the centripetal acceleration of AB. It is inwards, that is towards this center. So what I'll do here is, next thing would be drawing a line parallel to link AB. It would be pointing in the downward direction because here we know the direction, and at the same time the magnitude is known to us. It is 1.71. Now how to fit it into the scale, because 1.71 is in terms of meter per second square, scale is 4.64. So 1.71 would be divided by 4.64. I'll just show here. 1.71 divided by 4.64, and it will give me the value that would be in terms of centimeter, which would be marked over this. It comes out to be 0.37 centimeters. And remember, these are very lengthy methods, so you have to just follow the video up to the end so that you all can understand completely that how to draw the velocity and acceleration diagram. You all have to go through the video completely and wait till the end. Now this value is 0.37 centimeter. It means it will be somewhere around 3 mm, or we can say it is 3.7 mm to be exact, 3.7 mm or 4 mm. So here I'll mark from point A 4 mm distance. Now this small line indicates the centripetal acceleration for link AB. I'll just show it here with the help of an arrow. It shows the centripetal acceleration for link AB. Then its tangential acceleration would be perpendicular, and since the direction is pointing downwards, the tangential acceleration, it would be perpendicular and it can go towards this side as well or onto the other side. Now when I am going towards, for example, towards the right end, then I won't be getting any intersection point here. So it is better to bring this tangential acceleration towards the left side, because here the chances of intersection are there, so that we can get point B. So what I'll do here is, after getting the centripetal acceleration, I'll measure 90°, because centripetal acceleration and tangential acceleration are perpendicular to each other. So measuring 90° from this distance which I have taken for the centripetal acceleration, now measuring 90° would give me the sense or the direction of the tangential acceleration. So drawing a light line, light dotted line, now this line is showing the direction of tangential acceleration for link AB. The magnitude we don't have, it means we do not know where point B would be there on this line. For that we can go for the other link, which is link CD, as we can see here. And for link CD, now CD is also, we can say that here this link CD is oscillating, it is oscillating, we can say, about point D, but in the problem they have not given the rotation, that is, in the problem they have given the rotation of the crank OA. So we can say that the rotation of the crank is at point A, but they have not given any kind of rotation for CD, so we won't be taking its center as D, but the common center O. It means the centripetal acceleration would be in this direction, that is pointing towards O. Why? Because the rotation of CD with respect to point D is not given. It is just oscillating about point D, but the centripetal acceleration would be pointing towards the common center. That we have to remember. So this arrow indicates the centripetal acceleration for link CD. Now I know the direction of centripetal acceleration. So what I'll do here is, here we are having point O and D which are fixed. So drawing a line parallel to the centripetal acceleration, here is the centripetal acceleration of CD. So from point D, just again drawing a dotted line, and this dotted line shows the centripetal acceleration for link CD. Now its magnitude is known to us. We can say link CD is having centripetal acceleration as 7.14 meter per second square. Now I'll fit this into centimeter. So for that, 7.14 divided by the scale, which is 4.64, will give me the value in terms of centimeter, and it comes out to be it is 1.54 centimeters. So on this line which I have drawn parallel to the centripetal acceleration, so now on this line which is showing the direction of centripetal acceleration for link CD, I'll measure the distance 1.54 in terms of centimeter. 1.5 just slightly ahead of it. So here this line shows the centripetal acceleration for link CD. Here is the reference point. Now its tangential acceleration would be perpendicular to this point, or we can say to the centripetal acceleration. So drawing a line perpendicular to this point, now when I would be drawing the perpendicular, there are chances that the perpendicular line which I am measuring, it can go down or it can go up. If it goes down, then we won't be getting any intersection point. So the direction of tangential acceleration for CD has to be upward. So when I have measured this 90-degree angle, drawing a dotted line, now this dotted line which is going up is showing the tangential acceleration for length CD, and where this tangential acceleration of CD is cutting the tangential acceleration of AB, I am going to get point B. So this is the way in which it should be drawn. Actually, I would be getting point C here. Remember, because here we have point D, and then this would be representing, I'll just show it here. We are getting point C here and not point B, because at present the intersection of CD and this line, which is the tangential acceleration of AB, also the tangential acceleration of AC is also along the same line. So I can say that the direction, this equal to sign which I am showing, it is not indicating the magnitude. Remember, I am just showing it for the direction, that is the tangential acceleration of AB and the tangential acceleration of AC are along this same line. So after getting AC, on this same line I would be extending to get point B, and for that I'll again use the concept of similarity like I have used for the velocity. And the concept would be, in the velocity diagram I had taken AC upon AB, capital. So similarly here also, capital AC upon capital AB is equal to small AC upon small AB, small AC upon small AB. Capital AC by AB is 450 by 550. And small AC I can measure it from here. And just for that I'll explain how to get this. Now we have the centripetal acceleration of, this is AC, and here I am joining this A to C distance. So this is the centripetal acceleration of, here I can say this is AB, and then here we have the tangential acceleration of AB, or we can say it is along the same line for AC as well. So this shows the main acceleration of AC, and the direction is opposite in nature to that of centripetal and tangential. Now along this same line I am projecting a light line along the same line, light line. On this same line I am going to get point B. So measuring this distance A to C for the main acceleration, it comes out to be 7.2 centimeter. So AC is 7.2, and finally from this AB value would be, I'll just find the value here, that would be it is 8.8 centimeter. That is AB distance, I am getting it as 8.8 centimeter. So on this same line I have extended it, measuring the distance 8.8 with respect to point A. This gives me point B. Now after getting point B, the next thing would be link BE, and its centripetal acceleration will also be pointing towards the same common center. So for link BE, its centripetal acceleration is pointing towards the center. So after getting point B, I'll draw a line parallel to BE passing through point B. So parallel to this link BE, drawing light dotted line. Now this line shows the direction of centripetal acceleration for BE, Its value is there in the table. It is 10.21 meter per second square. So converting it into centimeter by dividing with scale, so 10.21 divided by 4.64, it is 2.2 centimeter. So from point B, I'll measure 2.2 centimeter along this line because the direction is known. 2.2 centimeter. This shows the centripetal acceleration for link BE. Centripetal acceleration for BE. Now the tangential acceleration, we don't know the value, but it would be perpendicular to the centripetal acceleration. So just drawing a light perpendicular line through this point C, or here we have this point which I have taken it as 2.2 centimeter. So from that, not exactly on point C, there is some difference here. Measuring 90-degree angle. Now this light perpendicular line would be showing the tangential acceleration, but the concept here is centripetal acceleration. Tangential acceleration won't be going up because to get the intersection point, that is point E, this tangential acceleration should be in the downward direction, that is close to the fixed point O and D. So I'll say this downward direction shows the tangential acceleration direction for link BE. And how to get it? Here the last link which is left with us is the slider, which is slider E, and its acceleration would be along the line of stroke. Acceleration of slider E, horizontal. So already we have point O and D here. So just projecting light horizontal line so that it cuts this tangential acceleration. So drawing a light horizontal line through points O and D, light horizontal, so that it cuts the tangential acceleration for BE at this location. And where it cuts this line, here I am going to get point E. So this is the tangential acceleration for BE. Tangential acceleration for link BE. Similarly, here we had the centripetal acceleration of CD, and here we have the tangential acceleration for link CD. Finally, after getting point E, it would be joined with point B here to get its main acceleration or the actual acceleration of the link. Here is the centripetal acceleration of BE, and this is the tangential acceleration. So they are going into the same direction, but the main acceleration is acting like a resultant, so it would be in the opposite sense. This shows the acceleration of link BE. Then we have point C here. C would be joined to D to get the acceleration of the link CD. So I am joining C and D, and its direction would be, since centripetal acceleration is pointing towards this side, the tangential acceleration is also along the same sense. So the main acceleration should opposite because it is the resultant. So this shows the acceleration of link CD, the main acceleration. So this completes the acceleration diagram. Now in the question they had asked us to find the acceleration of slider E. So I'll write down that since acceleration of slider E will be equal to this horizontal distance OE, this shows the acceleration of slider, which is distance OE. Here I am writing this as acceleration of slider E. Distance OE into scale. OE distance, I'll measure it from here in terms of centimeter. It is 1.2 centimeter into the scale, which is 4.64. So remember, whenever we are finding the acceleration or the velocity, we have to multiply by scale, and if you want to convert the acceleration in terms of centimeters, you have to divide by scale. So therefore this acceleration of slider comes out to be 5.57 unit is meter per second square. So that's the second answer, and also the completion of the problem. These are very lengthy problems, we have to remember, and once again I'll explain that whenever you have centripetal and tangential acceleration, they are perpendicular to each other. Centripetal and tangential perpendicular to each other, and their resultant is the acceleration or the main acceleration of the link. So as said in the problem, we have found out the velocity and acceleration of the slider by using the relative velocity method, and then nothing extra is asked in this question apart from the velocity and acceleration of the slider. Once again, at the end of the video, I'll say that since these are graphical methods, the answer may change, the answer may vary from person to person depending upon the type of scale taken or the accuracy with which the diagram is drawn. So no two answers which would match perfectly when you are solving the problem related to velocity and acceleration in mechanisms. So that was the end of the problem. At the end, if you all find my videos helpful, you all can like, share, comment and subscribe our channel and share it amongst your family and friends. Thanks for watching.